Okay, let's go ahead and continue talking about how we can find the probability of an event E. Okay, let's assume that you've either given or have determined an acceptable probability assignment for all the simple events in your sample space. Then once you've done that, then we can actually give the probability of some event E using this notation as follows. If your event is the empty set, in other words it has no elements from the sample space, then the probability of that event is 0. If your event is simply a simple event, then we already talked about that up here. We've already determined and assigned a probability to it. If the event is a compound event, then to find the probability of the event, all we do is add all of the probabilities of all of the simple events that make up the event E. And then if for some reason E is the sample space, then the probability of E is just going to be 1, because that's basically everything. So if your event space is the sample space, then the probability of your event is the same as the probability of just getting something from the sample space, which is 100% sure thing. Okay, so let's look at an example, and we'll cover all of these in this example. Suppose we select a 3-card hand from a deck of cards. Okay, we're going to assume that each 3-card hand is equally likely. So what we're going to do is we're going to assign the probability to each 3-card hand to be 1 out of the total possible hands. So that's actually going to be 1 out of 22,100. So in other words, there's 22,100, 52 choose 3 total possible 3-card hands, and we're going to assume that each 3-card hand has a chance of 1 out of that number of occurring. Now, let's say I assign the event that I'm looking for to get all red kings in a 3-card hand. Well, we know that that event is the empty set because you can't get 3 red kings. So therefore the probability of that event would be 0. So there, that corresponds with A up here. Now let's assume E is the event of getting a particular 3-card hand, like the 5, 6, and 7 of hearts. Well, that's a simple event. So E is a simple event, and as I said up here, it's already been assigned. So that probability is 1 out of 22,100. Okay, let's look at a compound event. Let's let E be the event of getting a hand with 3 aces. Well, there's actually 4 ways that can happen. And each of these 4 ways has the same probability, 1 out of 22,100. So the probability of that occurring would just be the sum of those 4 probabilities. And you add those 4 probabilities up, and you get 4 out of 22,100, which you can reduce to 1 out of 5,525. And then finally, let E be the event of getting less than 4 kings. Well, the most kings you can get in a 3-card hand is 3. So every 3-card hand in the sample space is going to have less than 4 kings. So in this case, the event space is simply the entire sample space. And so the probability of that occurring is equal to 1. So the steps for finding the probability of an event are right here. You set up the sample space. You assign acceptable probabilities to the simple events. And then to obtain the probability of an event, suppose it's a compound event, you just add the probabilities of each simple event. So here's an example. Suppose we roll a pair of 6-sided dice and observe their sum. Well, we've already previously observed that there's 36 possible rolls. So I'm going to assign the most basic probability to each simple event, which would just assume that each one's equally likely to occur. So the probability of each simple event, I'm going to just say, is 1 out of 36. So the probability of any simple event is just 1 out of 36. So now let's just state some event we might be interested in. What if we're interested in the event of rolling a sum of 5? Well, if you look at this, there's actually, you can roll a 1-4, a 4-1, a 2-3, or a 3-2. Well, so that's 4 simple events that make up that event space. So, and the probability of each of those simple events is 1 out of 36. So if we add up those 4 simple events, we'll actually get 4 out of 36, which is 1/9. So that would be the probability of rolling a sum of 5. Now, we're going to find out in a minute that if the events are equally likely, we can actually just count the number of elements in the sample space and then divide that by the number of elements in the event space, and then divide that by the number of elements in the sample space. So in other words, as long as I know that each of these simple events is equally likely, then to get the probability of E, I can just count how many elements are in the event space, which in that case was 4, and then divide it by the number of elements in the sample space, which was 36, and then of course reduce it to 1/9. So in many probability experiments, we do have this equally likely assumption. And as I said before, it just means that all simple events have the same probability. So if there are n simple events, each simple event has the probability of 1 out of n. And this is actually a theoretical probability. Now you can extend this rule to the following, and I've already given you the theoretical approach, but we can say the empirical approach actually says that the probability of an event under the equally likely assumption is that its probability is the frequency that E occurs over the number of outcomes in the sample space. So if it's a theoretical event, it's just the number of elements in the event space divided by the number of elements in the sample space. It's basically the same thing here, but we call this the frequency of occurrence rather than the number of elements. Okay, now to understand the difference, let me do an experiment here. Let's toss a single die. Now think about this. Casinos rely a great deal on the accuracy of a die. They expect each simple event in a die to be equally likely. So if you toss a single die, then the probability of each of these events occurring, simple events occurring 1 through 6, each probability would be 1 out of 6. Okay? But what if we think something's wrong with the die and we had a machine test the die by tossing it 10,000 times with the following results? So maybe we roll a 1 3,000 times, we roll a 2 1,000 times, a 3 1,000 times, a 4 3,000 times, a 5 2,000 times, and we never get a 6, so we get a 6 0 times. Well, 3,000 out of 10,000 is 0.3, so we could assign the probability of 1 of 0.3. 1,000 out of 10,000 is 0.1, so we could assign that probability 0.1 for 2, and then for rolling a 3, same thing, and then for rolling a 4, again 3,000 out of 10,000 is 0.3, and then the probability of rolling a 5 we could assign 0.2, and the probability of rolling a 6 we could actually assign a 0. Now notice that this probability distribution adds up to 1, just like these up here did. They add up to 1. Well, these add up to 1 as well. If you add all of these probabilities up, they're going to add up to 1. So basically that's the difference between up here we had a theoretical experiment, and here we have an empirical experiment. Now under normal circumstances, when we toss a single die, we'll assume that all 6 values are equally likely to occur. And if we toss a pair of dice, we'll assume that all 36 possible ordered pairs are equally likely to occur. So let's say we toss a pair of dice and we find that we already know from previous experiments that the number of possible rolls of a pair of 6-sided die would be, there's 6 ways the first die can land, 6 ways the second die can land, so that would give me 36 possible outcomes. So what if I wanted to find the probability of rolling a 9, sum of 9? Well, notice there's 4 ways to do that. 3, 6, 6, 3, 5, 4, 4, 5. Well, since each of these is equally likely, we can just say the probability of E is the number of ways to get my event over the total number of elements in the sample space. So it's 4 out of 36. So it'd be 1/9. What about the probability of rolling a sum of 7? Well, you could roll a 1, 6, 6, 1, 5, 2, 2, 5, 3, 4, 4, 3. So that's 6 ways out of 36, which reduces to 1/6. So that probability would be 1/6. Or what if I said rolling a sum of 2, 3, or 12? Well, you can roll a 2 with a 1, 1. You can roll a 3 with a 2, 1 or a 1, 2. Or you can roll a 12 with a 6, 6. So again, there's 4 ways out of 36 that event can occur, which reduces to 1/9. Now, these numbers, I won't get into the details, but these numbers are actually important numbers when rolling die. You might remember that if you roll a 7 in the game of craps right off the bat, you win, but if you roll the 7 after the first roll, you generally will lose. So I'm going to follow it up with an empirical example. Here I surveyed 1,000 drivers, and you can see there's 1, 2, 3, 4 different age groups, and then there's 3 different accident categories: 0 to 1 accident, 2 to 3 accidents, or more than 3 accidents. And each cell contains the number of drivers that are in each age group in each category. And I've also given you the totals of the categories to the far right and the total of the age groups at the bottom. So you may not have this given. You might have to figure it out for yourself in an example. Okay, so I want to know the probability that a driver will have more than one accident. Well, more than one accident would actually be the 325 drivers that have 2 to 3 accidents and the 100 drivers that have 100 accidents. So you add those two together and you get 425 out of 1,000, so the probability of that would be 0.425 in decimal. And then what about the probability that a driver will be in the 26 to 39 category, or, now or remember is associated with union, or have more than 3 accidents. So we really want the probability of the union of these two events, 26 to 39 or more than 3 accidents. And remember, the addition principle says to find the number of elements in a union, we add the number in the first set, which 26 to 39 is 200, and then the elements in the second set, which would be more than 3 accidents, is 100, and then you take away the number of elements that are in the intersection, and this 25 is in the intersection. So if I take 200 plus 100 and then subtract 25, I actually get 275 out of 1,000. So that reduces to 0.275. The next one is actually says 40 to 55 category and have 0 to 1 accidents. Well, that would be an intersection for and. So you look for the 40 to 55 category and look where it intersects with 0 to 1 accidents, and that's going to be right here at the 250. So that's 250 out of 1,000, which is 0.25. The next one says we'll be in the 26 to 39 range or the 40 to 55 group. Well, that problem, there's no intersection there. So you just add the 200 here and the 400 here from the two groups, and you get 600 out of 1,000, which is 0.6. And then to find the number of drivers that are not in the 55 plus range, well, let's find out how many are in the 55 plus range, because that's easier. There's 100 in the 55 plus range, so that means there's 900 that are not in it. So the probability of that would be 900 out of 1,000, which is 0.9. Okay, one more experiment. We toss a die 500 times, and it lies on its flat side 400 times, its edge side 75 times, a domino, I'm sorry, not a dice, and it's in 25 times. And so these are the probabilities that we get. 400 out of 500 would be 0.8, 75 out of 500 would be 0.15, and 25 out of 500 would be 0.05. And that's an empirical example based on an experiment that we did and the results and data that we collected. I'm going to go to another video, but before I do, freeze the video and read right here the probabilities that I've assigned to these possible rolls of the die. And you'll notice that this one is pretty low, and this one is pretty low. So in that case, we might consider throwing those die away and getting some more die to use for our experiment.